All right. The next talk is Inferring Ranked Dialog Flows from Human-to-Human Conversations by Javier Sastre and Aisling Mugen.
Thank you. So welcome back. So one of the problems that we have been working on as well in Accenture is to try to determine what are the typical sequences of questions and responses a human agent makes in order to provide a specific service. So assuming that you have already managed for each one of the conversations to transform each one of the sentences into a normal form, having these sequences for each one of the individual dialogues in normal form, a potential way of building a dialogue flow from these sequences would be to simply merge all the bubbles that are labeled with the same type of question and response, obtaining something like this. But this trivial approach has a few problems, starting with the overgeneration problem. So for instance, here to the left, if we merge these two bubbles labeled with the letter B, the dialog flow at the right is going to be represented as well the sequences ABE and DBC, which are not present in the original data set. And potentially when a conversational designer is going to be looking at this dialog flow, they could get confused. And here we have another more drastic example, where by merging these two A bubbles and B bubbles, the dialog flow is representing a conversation that just contains sentence A or B, whereas both sentences were necessary. And also it's producing this infinite looping here that was not present in the original data. And a third problem is that when you compute these dialog flows on actual call center data, you end up with this huge dialog flow where it's difficult for a human to find what are the actual sequences that seem to be the most frequent. So we need some sort of strategy that is going to be able to, from one side, to try to limit the overall size of the dialog flow, or potentially to be able to split this dialog flow in smaller dialog flows containing, for instance, the top 10 paths in the conversations, and then the next best top 10 paths and so forth. So the conversational designer would be able to start reviewing the most relevant paths, and if they consider it necessary, they can continue reviewing the next dialog flows and so forth in some sort of visualization with pagination of dialog flows. And well, summarizing the approach we have been working on is based on finite-state automata. So we are coding each one of these sequences of questions and responses as linear automata. So here in the transitions, we are annotating the agent sentences. And well, optionally, we are also annotating the potential customer sentences in the states, just to also provide a few examples of customer sentences that would allow to understand what did it trigger for the agent to say one thing or another one. And we are going to minimize this automata in order to collapse the common subsequences between the different conversations. Then with another algorithm, we are going to annotate the transitions with frequencies and probabilities. And then there is a final algorithm that is going to rank the different paths and label the different transitions with the rank of the best paths they belong to, and also prune this automata to a desired maximum amount of paths. Now, well, now we'll continue with Aisling, who is going to explain the first steps.
Thanks, Javier. So yeah, I'm going to bring you through the first few steps in our approach. So how we represent a set of dialogues as finite-state automata is as follows. If we have, for example, 4 agent utterances, A, B, C, and D, with dialogues that are ABC, ADC, and BDC, we can build the non-deterministic finite-state automata, or NFSA, as you see on the right here, where the agent utterances are in the transitions between states, and then we use the states to concatenate the agent utterances that occur between 2 agent utterances and put them there in, as you can see, in lowercase letters. So for the minimization step, the motivation behind doing this is if we have, like Javier showed, a really big set of dialog flows. We want to represent the same information in as few states as possible. And so as you can see here, the three dialogues are represented in the minimized automata on the right here with much fewer states. And so to perform this minimization, there are 4 steps, which I'll take you through in more detail now. But they are first reversing the automaton, then determinizing it, reversing it once more, and then finally determinizing again. And so what determinizing means essentially is collapsing 2 states that are the same into one. And one thing to note here, an important consequence of performing this minimization is that the resulting automaton is deterministic. What that means is that only one state can be reached by consuming a given input subsequence. So the first step is straightforward, and visually you can see here the arrows change direction, and we swap the initial states to final states and final states to initial. The second step then is this determinizing step. So as you can see here, the state or 0 in the determinized automaton represents the states Q3, Q7, and Q11 as the transition C has been collapsed in all 3. And just one insight into our initial implementation of this work, and we try to keep track of the transition frequencies, as you can see here in gray. But as you'll see in the final step, this actually is not possible. And so we have to add a step after the minimization to do this. So the third step then is simply reversing the automaton. And finally, one more determinizing, this time from the top down. So as you can see here, the state or 3 from the automaton on the right, on the left, has been split across 2 transitions in the minimized automaton, and this is why we cannot use the keep track of the frequencies of the transitions as we perform these steps. And so to be able to efficiently transfer the data, like for example, the transition frequencies from the original NFSA to the minimized DFSA, we compute a topological sort. So what this is if we assume states are tasks and transitions are task dependencies, we must order the tasks so that no task appears before one it depends on. So for this automaton, there are 2 options for the topological sort. They're S0, S1, S2, S3, S4, or S0, S2, S1, S3, S4. So for example, you cannot traverse to S3 until both S1 and S2 have been visited. So how we compute this? We first annotate each of the states with the number of incoming transitions, as you can see in green, hopefully. And so we start off with the first initial state, S0, and we consume each of its transitions. And every time a target state has been reached, we -1 from the counter of that target state's incoming transition frequency counter. And if that counter comes to 0, you add that state to the queue. And you repeat this process until there are no more states in the queue. So what this topological sort allows us to do is to traverse the minimized automaton in the most efficient way possible, while in parallel traversing the equivalent states in the original NFSA, and to be able to keep track of both at the same time, to take the transition frequencies and also the customer utterances and overlay the data from the NFSA to the minimized DFSA. So now that we have the frequencies, something we can do now is actually convert these into probabilities, which will help us with the ranking of best paths, which I'll pass back to Javier to start talking about. Thank you.
So now for the final step is about, from one side computing from a potentially big automata, what are the top K paths in the automata, and also rank the different transitions in order to know which transitions belong to which top path, so we can enable this visualization with pagination. So for this algorithm, I'm going to use this automata as an example. and we are going to extract the top three parts of the automata. Okay, so first step is to add a new state that is going to be the new and unique final state, so that we can compute the top paths between initial state Q0 to final state Q7. And then we start by annotating Q7 with a top score so far of 0. We are going to be propagating this top score to the right, aggregating the frequencies in the transitions as we propagate these top scores forward. So for instance, here we have this top score of 0 plus this 1. We annotate Q1 with a base score of 1. That has been possible by means of this last transition from Q0 to consuming A. And then the same thing for this transition at the bottom. And here we have an example where we are not only producing one top score, but we have two top scores, this new one resulting from this transition here. And so forth, we are going to be propagating and propagating until we arrive to the last state. And here we have a situation in which this list of top scores overflows, and we have more than the target of 3 top scores. So in that situation, we simply remove the excess. We are going to remove the lowest scores. And well, for a real case where this automata is going to be much bigger, we would not be propagating, but at most top scores. And that way we are going to avoid an exponential worst case cost of execution of this algorithm. Okay, so once we have propagated all the scores, now we know that score 7 is the best one, then it's 6, then it's 5. So we have these ranks in here, and we are going to propagate these ranks backwards up to state Q0. So for these 3 scores, it was this transition who allowed for obtaining them. We are annotating this transition as belonging to all the 3 paths, and then propagating these ranks again to this score list and continue propagating backwards in this fashion. So in this case here, we see that Q5 didn't receive any rank. All the ranks went upwards. So this is going to be marked for deletion. And in this situation here, we see that there are 2 ranks that are flowing downwards, and the other rank is flowing to the left. And well, if we continue, we arrive to this situation where finally all these 3 ranks have arrived to the initial state of the automata. So with that, the backward propagation is concluded. So now for the cleanup, we remove the states and transitions that didn't receive any top rank. We remove this artificial additional state that we added in order to get back the remaining original final states. And then we can get rid of these lists of top scores, which are no longer necessary. So once we have this automata with the transitions labeled with the ranks of the paths they belong to, doing a visualization with pagination is straightforward. So imagine if we want just to look at the best paths from the first to the second one, we simply need to traverse this automata from state Q0 through all the transitions that are labeled with ranks from 1 to 2. And we would only be exporting that to present it to the user. And then if we click on, OK, show me the next page, the next batch of best paths, we would just need to traverse the automata again and only export the paths that belong to rank 3. OK, so far we have managed to condense this potentially big list of sequences or of sequential automatons into a condensed representation. We have managed to prune it, and we are able to only export certain ranges of best paths. But still, we are annotating each one of these states with every possible customer sentence that may happen between 2 agent sentences. And potentially this list is going to be very big and is going to produce big customer bubbles. So we can use some strategy in order to keep, to limit the amount of customer sentences as follows. So for each set of customer sentences in one of the vowels or states, we encode those sentences. We clusterize them in order to find groups of semantically similar sentences. And for each group, we are just going to select one example, the one that is the closest to the cluster center. And in case we have yet too many clusters, we can simply keep the bigger scale clusters, which are going to correspond to the most frequent customer sentences. Okay. Okay, then another problem that we had with this approach is that the way in which we are building this automaton and merging the common paths, all the customer sentences that can be starters of conversations, they are getting together in one single bubble, resulting in a dialog flow like this. But then we have here several potential first agent sentences, and we don't know exactly which customer sentences did trigger each one of these agent sentences. So we would like to split this customer bubble into groups for each one of these first agent bubbles. And we can achieve this by simply modifying the original automata that we have built. We are duplicating the first agent transitions and putting them before the customer sentences. That way, when we apply the minimization algorithm, these two customer sentences, we will be able to merge them together because they are both preceded by an A. But we will not be able to put this I together with the A and E. And then this E is going to be left alone. And we just need to clean up the duplicated agent sentences. And we get a dialog flow that looks like this. So you can see that now there is a customer bubble for each one of the agent bubbles. And well, as conclusion, so we have presented an approach that manages to condense sequences of questions and responses from human-to-human conversations, well, from the agents, in order to produce dialog flows whose size can be limited, or that we can export different subsets of these dialog flows using a pagination method, so that later a conversational designer can review and then use it as inspiration in order to create a conversational agent. Okay, and well, as future work, this splitting of the customer bubbles at the beginning of the conversations, we could also do the same across the entire dialog flow, so that the customer sentences not only correspond to possible responses from the customer for an agent sentence, but we will also see what can be specific customer sentence triggers for the next agent sentences. Then it would also be interesting to identify substructures in these conversations. Well, you can imagine that a human agent, when it's providing a service, it's going to follow certain phases. Like we start with a phase of trying to authenticate the user, try to identify who is this user, make sure that it's this person and not a different one, and he has the rights to access this particular service. And then they are going to ask for a certain amount of information and finally provide the service. So if we were able to identify these subsequences within the full sequences, we could create dialog flows for each one of these phases, which could result in more compact representations of the dialog flows. And well, finally, perhaps it would be interesting to allow for some certain control over generation or noise in the automata, so that we can produce automata that are even smaller, but well, at least having certain control on the amount of noise that is being produced, so that the resulting paths are not too confusing for the conversational designer. That's it. Thank you.
Questions about this? You said it would deep dive in this session, so that's what we got. I have a question about there's a lot there. My question is about if it algorithm efficiency. Are we there yet? Okay. Algorithmic efficiency. So I saw kind of two stages, maybe there were more. The first stage is we have this kind of FSA or a bunch of FSAs, and we want to minimize those.
Yeah.
Right? And right.
Yeah.
Slide. So this stage, and then you have the next stage, which takes frequencies and kind of prunes off the unneeded parts. So those can be fairly inefficient. I mean, obviously you want to do this, so during the dialogue, it's as efficient as possible. So this inefficiency, I guess, is sort of taken offline, done beforehand. But are these both of these algorithms, like what kind of efficiency are you getting from these?
Well,
Does it scale well?
I would say that from the experiments that we have run with actual data, it took like maybe 1 minute to produce these dialog flows, and this is important because, well, this is actually coupled. This approach is coupled with semi-automatic approach for actually determining what are the types of questions and responses. Okay, so as we are analyzing the different types of questions and responses, we ask to regenerate the dialog flows, and well, it's an iterative approach. Okay, so yeah, speed was very important, and actually the part that is the most time consuming is the filtering of the customer sentences. Okay, the rest, the pruning was like one or 2 seconds for a case of generating 1,000 top paths, which I don't think that a conversational designer would be willing to look at all of them. Okay, but just to give a maximum limits, and maybe then the most expensive step would be actually to code all the sequences of types of questions and responses as these non-deterministic automata. But yeah, the part of minimizing the automata is very fast and the problem as well.
Other questions?
Hello, thank you for the talk. My name is Patrick from Alexa AI. I was wondering, how narrow does the domain need to be for an approach like this to be useful to analyze the data? Like, I imagine if you have like open domain conversations and you try an approach like this, where like both parties of the conversation can pretty much talk about anything. Like,
yeah,
do you think like does it work for like 2 domains? Does it have to be like within 1 domain? Like, how maybe you can give some insight into like how many different kind of agent responses there are in your data that you have been working with?
well, actually, we are using this approach for analyzing call center conversations, and in particular, first we determine what are the intents. Well, if you saw the talk that we had in the morning was precisely about figuring out what are the intents in conversations. And then from there, we are going to extract the subsets of dialogues for one specific intent. So you are already narrowing down the domain. And then these dialog flows are going to be computed for specific intents. And well, that's in the end, that's how do you design a conversational agent. So you decide what are your intents, and for each intent, you are going to have some sort of dialog flow or workflow on how the conversational agent can provide the service.
Thank you.
Thanks, speakers again.